Hello class, in this video I'll be doing another example on how to find inflection points and how to test for concavity. Let's begin. So we want to find the inflection points and any intervals where the graph of this function is either concave up or concave down. And to do that, we need to find the second derivative. And I've already gone ahead and provided the first. And since the first derivative is a quotient, I'm going to apply the quotient rule to find the second derivative. That's going to be the following. It's going to be the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, all divided by the denominator squared. And after the second derivative has been simplified and factored, you'll get this. Okay, so now remember that there are possible inflection points where the second derivative is equal to 0 or the second derivative does not exist. So what I'm going to do is I'm going to take the second derivative and I'm going to set it equal to 0. There's the second derivative. Set it equal to 0, and then I'm going to cross multiply. And when we do that, we get negative 2 times the quantity x minus 4 times the quantity x plus 4 is equal to 0. So that implies that there are two possible locations for an inflection point. One at 4 and one at x is equal to negative 4. Okay, now to see if the second derivative doesn't exist at any values of x. And my claim is that the second derivative exists for all values of x. And that's because x squared plus 16 is always greater than 0. So that means the second derivative is never undefined. All right, so there are no more possible locations of inflection points since the second derivative exists for all values of x. Okay, so now on to the intervals that we need to create. So let's go back to the original function. The original function is a natural log function, and the natural log function requires positive values for the domain. So since x squared plus 16 is always positive, the domain is all real numbers. All right, so now we're ready to write the intervals that we're going to test. So the first interval is going to start at negative infinity and then go to the smallest possible location of an inflection point. And in this case, that is negative 4. The second interval is going to be between the two possible points of inflection. And the third interval is going to be the largest possible location of an inflection point all the way to infinity. I'm just going to change up these colors real quick. All right, so now we are ready to test values of x. So in the first interval, -5 is in the interval -infinity to -4. So I'm going to test the second derivative when x is equal to -5. And in this case, I don't really care about the values. I just want to know the signs. So this is -2 times -9 times a -1. And we're going to divide that by a positive value in the denominator. And the result is that the second derivative is negative, which means the graph is going to be concave down. In the second interval, 0 is in the interval. So I'm going to test the second derivative when x is equal to 0. And in this case, it's -2 times -4 times a +4 divided by a positive number, which means the second derivative is positive, so the graph is concave up. All right, now since the concavity changed at x is equal to -4, we can conclude that that is the location of an inflection point. Now let's see if the concavity changes at x is equal to 4. Let's pick a +5. It's going to be a -2 times a +1 times a +9, all divided by a positive number. And the result is a second derivative that's negative, so the graph is going to be concave down. So that makes 4 another location of an inflection point, because the graph changed from concave up to concave down at x is equal to 4. Okay, so I'm going to go ahead and write down the intervals that the function is concave down. So the function is concave down on the intervals -infinity to -4 and 4 to infinity. Graph of the function is concave up on the interval -4 to 4. Now to get the inflection points. Okay, to do that, we're just going to substitute -4 into the function and +4 into the function separately. So the first inflection point is going to be at 4, natural log of 32. And the second inflection point is going to be -4, natural log of 32. And I'm going to box this and then show you that everything in this box is correct. Here we go. So there is the graph in Desmus. And I'm going to type in the 2 inflection points. There's the first one. And there is the second one. Now notice that the graph does indeed change concavity at these 2 points of inflection. It goes from concave down to concave up, back to concave down. So everything in this box is correct, and we are done.